You're looking at a giant sloth pelvis being chipped out of the Brea Tar Pits. It's been hiding here in Los Angeles, perfectly preserved for anywhere from 25 to 45,000 years. Scientists have spent more than a century excavating some 4 million specimens from the pits. But why keep adding to an already huge collection? Because each new fossil helps fill in the gaps on a 50,000-year timeline of life in the region, spanning to the end of the Stone Age. We went to the Brea Tar Pits to see how specimens are discovered, cleaned, and pieced together to build that record. The process kicks off with a sticky scavenger hunt. There are around 130 pits at the tar pits, which is technically a misnomer.
We don't technically have tar, we don't naturally have pits. What we actually have is asphalt, which is the crudest form of naturally occurring oil.
Some tar pits are still connected to their oil source, like this one.
So right now I'm in pit 91, which was the 91st pit. I know, fancy naming schemes.
Others become disconnected from their oil source and dry out. Huge dry chunks of the deposit are easier to move into separate boxes for excavation.
Right now I'm in box 13, which is 13 of 23, as you might be able to guess. This particular box has easily tens of thousands of fossils in it.
The excavation process isn't as simple as pulling a bone out of some goo.
So sometimes I'll find a fossil and be able to excavate it out in like 15 minutes. And sometimes I'm looking at a fossil for several months, definitely not dreaming about it, teasing me.
Take this saber-toothed cat skull, which has been weeks in the works. Based on 16 years of experience, Laura can estimate how many fossils are in a given deposit. To start her search, Laura first sets up a makeshift grid. This will help Laura keep track of where and in what position fossils are found, since the asphalt is too dense for traditional radar to provide initial images.
It's eyeballs and elbow grease.
Then she begins the meticulous process of carving the skull out of the matrix that encases it.
If I am confident that I'm not going to find fossils, I'll have things like hammers and chisels that I'll be able to get in there and move some of those things away.
This is where it gets tricky. Asphalt actually protects the bone's organic matter. This also makes them more fragile than traditional stone fossils.
Around the fossils themselves, we'll start with very small tools, something like this dental pick, which yes, is sourced from local dentists. Thank you for your donations. And sometimes I'm using it the same way that a dentist would, with the tip of it. And sometimes I'm using it more like a clay sculpting tool, kind of pulling sediment away from fossils. And then sometimes you also see me using a natural bristle paintbrush. I don't want to use plastic bristles because the oil will actually eventually degrade those bristles and they'll kind of melt a little bit, which isn't good for anybody.
Excavators tailor their strategy to preserve not only the delicate bones, but also the matrix itself. It's filled with valuable microfossils.
So we're going to pour that chemical solvent in there. So this particular one is a Novec 73DE, and so that's a chemical degreaser.
The solvent dissolves the asphalt and leaves behind treasures.
This one is the end of a tibiotarsus, or a drumstick. This one's bigger than a chicken. And we also have plant fossils as well.
Once the matrix is collected and surrounding sediment is cleared,
so I should be able to just kind of gently release the fossil from this tangle and send it on to the laboratory,
where preparators will put in even more hours into this one saber-toothed cat skull. To make sure our skull is shelf stable, preparators start with a more meticulous asphalt removal.
I would say that this could probably take me up to 10 hours in total to complete.
Stephanie uses more degreaser and a collection of cotton swabs, foam applicators, brushes, and picks to surface clean the skull.
When we have areas where there is jagged bone exposed, we prefer to use the foam tip applicators because there's no grabbing of fibers that could damage the fossil or transfer too much fiber onto the fossil. It's very much like painting almost.
The asphalt permanently stains the fossil a deep brown.
You will notice that as I work through this, the tool itself is changing color and becoming darker.
Now, her goal isn't to deep clean the specimen. It's to prevent deterioration over time. So some debris stays behind.
We leave the internal matrix in the skull because it provides structural support and stability.
If a fossil is damaged or comes out of the pit in pieces, it can be fixed.
So this is a canine from box 9, and we prepared this bit in September last year and sent it through to collections. And then in May this year, we found the tip, and when we put it in there, it was like a puzzle piece. So this is the lower jaw or dentary of a young direwolf that we have over here.
She uses a little adhesive and sometimes Japanese kozo paper to secure and stabilize the broken bits.
So kozo paper is a Japanese archival paper. You'll notice that I tore it, and we wanted to have these fibers. Think of when you walk into a spider web. It just feels like it's everywhere. They migrate and then catch onto the specimen and really anchor well onto it.
And the final step is covering the entire specimen in the same adhesive used for repairs. This seals and protects the organic material. If somewhere down the line a researcher needs to access that material,
Because we use acetone, it makes the whole process reversible.
after preparation,
The specimen there gets its own individual catalog number and then forms part of our already amazing collection that spans over 3.5 million specimens.
We have somewhere in the nature of at least 2,500 saber-toothed cats. So for instance, all of these drawers here are full of nothing but left upper arm bones of saber-toothed cats from just one of our about 130 deposits.
beyond saber-toothed cats, the La Brea collection contains around 4 million specimens from the last 50,000 years. And the biggest extinction event since the dinosaurs, the Ice Age extinctions, ramped up 12,000 years ago.
The majority of large mammals on Earth disappeared during this time. It's been really hard to figure out exactly when because we just don't have enough fossils.
These bountiful tar pits are an exception.
This is the only place on Earth where we have a time transgressive record over a 40,000 year period of many of these species. And this allows us to do research that you can't really do at any other fossil site.
Along with the when, researchers can answer questions about why species went extinct too.
Was it lack of water sources? Was it an area getting too hot or too cold? Was it increase in fire? Was it something to do with the arrival of humans on the landscape?
Some unique specimens can tell us about an entire species' behavior, almost entirely on their own. Take this elderly saber-toothed cat with hip dysplasia. The fact that it exists at all
is an indication that this species was probably social, because individuals with injuries or pathologies like this probably wouldn't have been able to hunt for themselves and probably relied on a social group or a family group to support them.
While the lab pieces together specimens, collections pieces together data.
Understanding what sort of processes might have been happening during the last major extinction event could be really important for helping us to weather some of these unprecedented in kind of human history impacts that we're experiencing. And there is basically no more important question to be asking today.
Knowing how creatures lived amidst climate change in the past might help humans learn to navigate extreme conditions in the future, like wildfires or droughts. In this case, the more we have, the more we know. And there are no plans to stop digging anytime soon.